This is our torsion setup. We have our experimental setup and then the computational data collection area. So our main on-off switch is this red switch that we dial to our on and off position. We usually turn the machine on approximately 30 minutes before our first experiment. Here you can see our brass sample already ready and placed into the experiment. The first two things we're going to do is measure the gauge length of the specimen and measure the diameter of the specimen, and this will help us in calculating our shear modulus within this experiment. So first we're going to measure the diameter of the specimen. In this case, the specimen is about 0.374 inches. Next, we're going to measure the gauge length of the specimen. And this specimen's about 3.2945 inches. Once we have those two dimension specifications, we can finalize the setup of our experiment, and we clamp the front and back end of our setup, while the front end will clamp that stationary section. The back end will clamp essentially our box for what holds our specimen, or the track. So then we can mark a straight line on our specimen to show the initial starting point of our specimen being straight, and as the test proceeds, we'll see that that line makes circular formations, and then we'll be able to notice how many rotations our specimen makes before fracture. Next, we can close the safety region of our specimen once our entire setup is accomplished. And you'll see on the screen built into the machine, we have a notification for tear, which is essentially zeroing our specimen, and then we also have a setting for speed. In our case, we have 4 settings: 50 degrees per minute, 100 degrees per minute, 200 degrees per minute, and 500 degrees per minute. In this case, we're going to select 200 degrees per minute. So we'll open the software section of our experiment, and in this case, this is the section that will calculate and obtain the numerical data. We can input the diameter and the length of our specimen of those values that we obtained earlier. And once we have these values, it'll allow us to have our numerical specimen available for the exact specimen we're working with. So you'll see the same setup we placed on the screen section. So we have the 200 degrees per minute set, so we can do it in a clockwise rotation or a counterclockwise rotation. In this case, we have a clockwise rotation. Once our setup is complete, we can then begin the experiment on either the computational side or on the experimental side. In this case, we're starting the test from the experimental side. And now we'll be able to watch our torsion experiment until fracture. Once fracture has occurred, we can open the safety section after we stop our test, and now we can remove the specimen from the clamp sections of the experimental setup and look at the fractured region of our sample. So once we loosen those two clamp locations, we can move the clamp section back on that track, and now we can remove and look at the fractured region and the specimen as a whole once it has been broken. So now we want to get the computational data that was collected during our test. So the computational section gives us a representative graphical section of our data, so it gives us the representation you see here. And then we can also save the numerical form. So first we're getting a screenshot of that graphical representation, and we'll save that, and then we'll get the numerical data. So once we get the option to save, we can save the file name. Once we decide what we want our specimen to be called, we can save our first section here, and then we'll get a second dialog box that shows up once it's saved that asks for a name and a comment. And we can also write the same thing here, but it does want us to fill in both of these items as well before we can save the test. So now once it's saved, we can open up the data or text file, and it gives us angle of twist in degrees, our time step. It also gives us our torque or torsional moment. And then once that first sample is completed, we can now complete a sample on aluminum. So we'll have the same process. We'll measure the gauge length and the diameter of the sample, and then we'll save the numerical data as well as the graphical representation that is printed out with the computational setup.